Welcome back. The title of this lesson is called Table of Trig Values for Acute Angles around the Unit Circle. All right, so this is probably one of the most important lessons in all of trigonometry, and I do mean that literally. We've learned about the concept of the sine and the cosine and the tangent and the secant, the cosecant, and the cotangent. We've learned about all that. We know how to calculate them. But there's this thing that's going to pop up over and over again, and it's called the unit circle. And a lot of students, when they open their book, they see the unit circle, and it looks really, really complicated. It's a circle, it's got lines everywhere, it's got square roots everywhere. It looks like a nightmare, even to me, and I already know what it means, okay? So what we're going to do in this lesson is we are going to get so comfortable with this unit circle that you can, go to sleep with it under your pillow at night and just be best friends with it because you're not going to be afraid of it. You will understand it, you will have it in your mind, and you'll use it as a tool, which is what it is supposed to be used for. So in this lesson, we're going to talk about the unit circle, and we're going to fill out a gargantuan table of trig values. So here we have the theta column. We're going to put angles in here all the way to 90 degrees because we're only going to be talking about acute angles in this lesson, up to 90 degrees. In future lessons, we'll go all the way around the unit circle to 360 degrees, but let's crawl first. Let's go only to 90 degrees. And then, once we put those angles in here, we're going to write down the sine of those angles, write down the cosine, write down the tangent, write down the cotangent, the secant, and the cosecant, and we're going to get very, very familiar with those critical angles, 30 degrees, 45 degrees, 60 degrees, 90 degrees, all the way up to 90, and then we'll save the rest of the unit circle for later. So we are going to build this table of values, and in the process of building this table of values from scratch, we are going to get very comfortable with this unit circle. The only thing I have labeled on this unit circle are the degree marks. You already know what this is. We've covered it before, 30, 45, 60, and 90. We're only going to really be talking about these values in this lesson here. But then in future lessons, we'll continue all the way around to the all the way around 360 degrees of the unit circle. But we need to start to crawl before we can walk. Now, the fundamental thing that I want to remind you of is that this is a unit circle. That means that the radius of this circle is 1 unit. So you can call it 1 meter if you want, or 1 inch, or whatever. It doesn't matter what unit of length, but it has a radius of 1. That means the distance from here to here is only 1 unit. The distance from here to here is 1. From here to here is 1, from here to here is 1, and of course, through all the diagonals, the distance is 1 unit away. And so you have 30, and then you have 60, and you have 90, and then we can go around the unit circle. We've done that before. And then between 0 and 90, we have it split into a 45-degree angle that cuts this in half as well. So in most books, you will flip to a page of the unit circle, and it'll have these degree markings, but it will also have the radian markings. I told you, I don't want to hit you too hard. We're going to cover radians later. Right now, just focus on degrees because we all can visualize degrees. But those books will also have values going around the outside of the unit circle with tons of square roots and all kinds of things. It gets very confusing. So what we're going to do in this lesson is we're going to build our unit circle. It's completely blank, but by the end of the lesson, we will have the whole thing filled out, which will correspond to the table entries that we have right here. And we're going to do the calculations for every single part of the unit circle that we talk about here. And so by doing it and by building it from scratch, you will be less intimidated. You will get a lot of practice with calculating things. And by the end of it, you'll know exactly what it means. Now, before we do the calculations, I want to actually do a computer demo for you to show you what we're actually doing. This is a unit circle. The distance between the center to the edge is 1. So if we walk this to the 30-degree mark, when we say, what is the sine of 30 degrees? Because the distance here is 1, right, to the edge. When we say, what is the sine of 30 degrees? Remember, I told you sine of an angle is the projection in the y direction. Sine goes with y. Cosine goes with x. So when we walk to the 30-degree position and we take the sine of this angle right here, what we're doing is we're saying, hey, what is the opposite side of this triangle? If I were to draw a dotted line down here, what would the projection of this hypotenuse be on to the vertical, on the y-axis basically here? What would the length of this thing be right here? That is called the sine of the angle. It's the projection in the y direction. When we take the cosine of 30 degrees, we're shining a light down and we're looking at what is the projection down here along the x-axis. So when we take the cosine of this 30-degree angle, we're saying, what is the distance right here? When we take the sine of this angle, we're asking, what is the distance right here? And every angle around the unit circle, we're doing the same thing. If you look at 60 degrees, if I want to know the cosine of it, I'm looking at the shining a light down, the projection down here on the x-axis. If I want to know the sine of 60 degrees, I shine a light this way, and I figure out, or this way, however you want to look at it, what is the projection of this hypotenuse along the y-axis? Sine goes with y, cosine goes with x. So you have to have that in your brain. To help you visualize that, let's walk over and do a quick computer demo to show you what I mean. Every point on the unit circle, when we take the sine, we're just looking at the projection on the y-axis of that position in the unit circle. When we look at the cosine, we're just looking at the projection on the x-axis of that position in the unit circle. Okay, welcome back to the computer demo. This is our handy-dandy unit circle. Notice that the radius here, there's a 1. It may be hard to read, but the distance from the center of the circle over here to the edge is 1 unit. 1 unit. This is a -1, means it's 1 unit from this way and so on. So it's a unit circle. The arrow is pointed at the 0 degree position. Now, let me increase the position of this arrow and show you what has happened. Let's go up to around 45 degrees or so. Or let's look at something right around 45 degrees. It says theta equals 45 degrees. I can't get it exact, but this angle theta measure right here is around 45 degrees. The blue arrow down here is the projection of this black hypotenuse onto the x-axis. If I could envision a flashlight above shining down and casting a shadow from this hypotenuse down onto the x-axis, that's what the blue arrow is. That is what is called the cosine. Notice the cosine of this angle, 45.383. Down here, the cosine is 0.702 and then a million decimals after it. And the sine is 0.7115 and so on. The sine is if I take a light over here and shine against this hypotenuse and look at the projection, look at the tip of this arrow, the projection on the y-axis is the red arrow. So the sine of this angle as I spin around is the red arrow, and the cosine is the projection of this thing onto what here is the blue arrow. So as I increase the value of theta, notice the red arrow is getting bigger. The sine is getting bigger because as the angle theta gets bigger, the projection on the y-axis gets bigger and bigger. That is why the sine of this angle is much larger and the cosine is much smaller, because the blue arrow is the projection on the x-axis and it is physically smaller than the projection on the y-axis, which is the red arrow. So the sine is the projection to the y-axis, which is red, and the cosine is the projection down here, which is the blue arrow. Now, if I go back to 0, or let's go back to 0 here, all the arrows are lining up, and so what's going on here is the hypotenuse is right here along the x-axis, so the cosine here, which is the projection on the x-axis, is fully 1, because the entire hypotenuse lies on the x-axis, but notice that the sine is actually 0 because there is no projection on the y-axis there. But if I just give it a little bit of an angle, like a tiny little angle, like something like this, notice how the blue arrow is really, really big, and the sine, which is the red arrow, is really small. The cosine is very close to 1, and the sine is very close to 0 because the angle is so tiny, there is almost no projection on the y-axis, and all of the projection almost is on the x-axis. So as I move this arrow around, the blue arrow is the projection in the x-axis that shrinks. The cosine is getting smaller and smaller and smaller. The sine is getting bigger and bigger and bigger until eventually this hypotenuse of this triangle lies fully on the y-axis. And I'm not going to be able to get it exact, but that's pretty close. Notice that now the sine is very, very close to 1, and the cosine is just 10 to the minus 17. That's almost exactly 0 there because the theta here is not exactly 90 degrees. But you can see then, as I approach this position, the red arrow gets closer and closer to 1, and the cosine gets closer and closer to 0. Now, we're only dealing with angles in the first quadrant in this lesson, acute angles. So I just want you to kind of visualize what we're going to do here, but I want to give you a sneak peek. Whenever I go past the 90-degree position to the other side, what happens? Notice when I get over here, the projection on the y-axis, the red arrow, is still a positive number because the y-axis is positive up here. So the sine is a positive number. The cosine is the projection on the x-axis, which is negative over here. That is why the cosine is negative in this quadrant. And so then you can see as I spin around and go down below over here, what's going to happen when I get into quadrant number 3. The cosine is still going to be negative because it's the projection on the x-axis, which is negative. But the y-axis projection is the sine, which now in this case is negative, so the sine and the cosine are both negative. When I get over to quadrant 4, what do you think is going to happen? The projection of this arrow way over here is going to make it so that the cosine is a positive number, because now the projection is back to being positive in the x direction, whereas the sine, the red arrow, is negative because its projection is down below, so the sine is negative. So the sine and the cosine values can be negative or positive. But notice that no matter where I go around this unit circle, the sine and the cosine never get bigger than +1, and they never get smaller than -1. Why do you think that is? Because it's a unit circle. The circle only has a radius of 1. That means the projection on the y-axis can never be bigger than 1. The projection on the y-axis, just like on the on the x-axis, just like on the y-axis, can never be larger than 1, because the radius of the black arrow is always 1. So the projections are always going to be less than 1, no matter where I move around here. The sines and the cosines may be positive or negative in their projections, but the values will never be larger than 1. So as we go back to the board, keep this diagram in your mind. Keep in mind that when we're looking at the cosine, we're just projecting the tip of this hypotenuse onto the x-axis and measuring the result. And when we project on the y-axis, we measure that result. We call those projections the sine and the cosine of the angle theta. Now, I hope you've enjoyed the computer demo, which visually tells you what sine and cosine is. This circle has a radius of 1, so the projection of the sine on the y-axis is always going to be less than 1 or equal to 1. The projection of that thing onto the x-axis will also be equal to 1 or less. If you go all the way around the unit circle, they can be negative or positive, but they're always going to be less than 1. The absolute value will always be less than 1. Now, what we need to do is fill out this table of values. There's a lot coming in this lesson. There's a lot of numbers. I really need you to watch it all the way through and then maybe start it over and watch it all the way again. And I promise you, you'll get there. But in the beginning, it might seem a little overwhelming because I have to put all of this in one lesson or else it won't make any sense at all. All right, so what we have is a table here. We need to fill it out. We have some special angles that are important, and the very first one is 0 degrees. All right, after 0 degrees, all over there on the unit circle, the next most special angle is 30 degrees. And then after that, we all know that the next most special angle is 45 degrees. And then after that, the most special angle is 60 degrees. And then after that, the most special angle is 90 degrees. Now again, we're only talking about acute angles, so we're only going up to 90 degrees. Later lessons, we will continue around the unit circle and talk about what happens to all the sines and cosines when you go all the way around. I don't want to talk about that. I only want to stop at 90 degrees. So the most important numbers are 0, 30 degrees, 45 degrees, 60 degrees, and 90 degrees. Everything else actually around this unit circle can be understood by just understanding these angles. So once you understand these angles, then everything else all the way around the unit circle is actually very easy to understand because it all comes from this. So let's take a look at the 0 degree mark. What I want to do actually is remember sine and cosine are the most fundamental one of these guys. They're fundamental and they're the most important of all of them. And then everything else can be calculated from sine and cosine. So we're going to fill out sine and cosine kind of from just kind of telling you what it is. The rest of these things, we're going to calculate them from sine and cosine. Before I do that, I want to talk about one thing that's really important, actually. So I'm going to put it over here as a separate note. It's so important, I want it to be up here at the top, right? We know that that the sine function is the opposite over the hypotenuse, so we already said it's y over r, right? We know that the cosine function is equal to the adjacent over the hypotenuse, which is x over r. Well, that's all comes from our triangle. Now, we all know that the tangent function, when you remember that triangle, was opposite over adjacent, y over x, right? But also there's another way to calculate tangent. I told you all of these trig functions from here on, the tangent and everything all comes from sine and cosine. And that's because in reality, the tangent function can also be written as the sine divided by the cosine. So if you know the sine and the cosine, you divide those two things, you automatically have the tangent. You might say, how is that possible? We know that tangent's opposite over adjacent. That's what you told me. But really, look at what's going on here. If what I'm telling you is true, then if we put the sine in the top, y over r, that's what sine is, and we divide by the cosine, x over r, then we have a fraction divided by a fraction, y over r, change this to multiplication, flip this over, r over x. The r's then cancel, and what you get is y over x, which is opposite over adjacent. So what I'm telling you really is I didn't mention it in the beginning because it wasn't important, but we're going to use it in this lesson. The tangent function can be really calculated two ways. You can think of it as opposite over adjacent, rise over run on your triangle. Sure. You can also calculate it by just taking the sine divided by the cosine. This guy right here is so important that I'm actually going to kind of box it for you. The tangent of theta is equal to the sine of theta divided by the cosine of theta. This is another one of these trig identities that pops up everywhere. And it works out because if you take the definition of sine divided by cosine, you get opposite over adjacent back. So what we're going to do in this lesson is I'm going to give you the values for sine and cosine, and I'm just going to write them down. But the rest of the table we're going to calculate based on the sine and cosine values. So really you only need to know sine and cosine to get this entire chart here. So let's go through and let's first take a look at 0 degrees. Let's go take a look at 0 degrees. I want to get it into the table and then I want to show you some things here. 0 degrees means my hypotenuse of the triangle really lies along the x-axis here. What do you think the sine is going to be? What is the projection of this triangle here? If it's really along this axis, what is the projection along the y-axis over here? Well, if the arrow, if you think of the computer demo, is this way, there's no projection at all on the y-axis. So the sine of 0 is the projection on the y-axis here. It's just going to be a value of 0. But the cosine is the projection here, if I shine a light from above, the projection onto the x-axis. But the entire thing lies on the x-axis. So the projection of this hypotenuse on the x-axis is 1, because the entire hypotenuse lies on the x-axis. Now let's go up to the 30-degree position right here. This is the part where you just have to believe me for a minute, and then I'll kind of show you that what I'm saying is true in just a little bit. If you go to the 30-degree position, the projection down to the x-axis and the projection to the y-axis are called the sine and the cosine. Now there are a couple things I need you to remember. Sine of 30 degrees, sine of 30 is 1/2. Sine of 30 is 1/2. I'll say it again. Sine of 30 is 1/2. Sine of 30 is 1/2. And you just have to keep saying it until you remember it. Sine of 30 is 1/2. So if you go over here to this table, the sine of 30 degrees is, what did we just say it was? It's 1/2. 1/2. What does that mean? That means if you look at this arrow that I have, the sine is the projection on the y-axis. If you shine a light this way and a dotted line right here, look at where it lands. It's about halfway up. It's exactly halfway along the y-axis. That's why the sine of 30 is 1/2. All right? Now let's project down this direction. When you look at this guy, shine a light from above, and you draw a little dotted line down here, the projection down here, what would this distance be right here? Now here's where you kind of have to just believe me for a minute. The cosine of 30 is the projection on the x-axis. It's the square root of 3 divided by 2. Now, square root of 3 over 2. You might say, that's a crazy number. How do you know that's what it is? Actually, just give me a second and I'll prove to you why it's actually equal to the square root of 3 over 2. But when you go and look in a calculator and actually calculate, you know that the number 1/2 is equal to exactly 0.5, right? Well, the number square root of 3 over 2, if you put the square root of 3 and divide by 2 in a calculator, what you're going to get is something like 0.866. Now, the decimals continue to go. I'm rounding here, but it's 0.866. So in other words, it's bigger than 1/2. So what we're saying is that when we look at the 30-degree position, the sine of it is the projection on the y-axis. It's 1/2. The cosine of it is the projection down here. It's about 0.866. That's bigger than 1/2. So from the diagram, it looks like it makes sense, but I'll still have to prove to you why it's square root of 3 over 2 in just a minute. So the sine of 30 is 1/2. The cosine of 30 is square root of 3 over 2. That is a very important number you need to remember. Remember, sine of 30 is 1/2. 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 Keep saying it. You need to remember it. The cosine of 30 can't be 1/2. It has to be something different. The other special number is square root of 3 over 2. So that's what you have to remember. Now let's move from the 30-degree position to the 45-degree position up here. Now, if you think about it, if I take the sine of this, I'm going to project it along to the y-axis. It's going to be up here somewhere, a little dotted line projection, something like this. Now, if I take the cosine, I'm going to shine a light down, the projection will be down here. So this distance will be the cosine, and this distance will be the sine. These distances are exactly the same, right? Why are they the same? Because 45 degrees is a special angle. It slices the 90 degree exactly in the middle. So whatever this number is, it must be the cosine and the sine must be the same number because the projections are the same distances, all right? What is that special number? The sine of 45 degrees is the square root of 2 divided by 2. I know it's a weird number, but that's what it is. And the cosine has to be the exact same number, square root of 2 over 2. Now these numbers that we have here, 0, 1, 1/2, square root of 3 over 2, and square root of 2 over 2, honestly, those are the only special numbers in trigonometry. Everything else in this table, it's going to look really crazy, but it all comes from those numbers. And in fact, the core idea of being able to look around the unit circle and figure out what the sines and cosines are, they're all going to come back to these 4 numbers, or whatever it is, 5, 1, 2, 3, 4, 5 numbers. 0, 1, 1/2, square root of 3 over 2, square root of 2 over 2. That is honestly the biggest thing I can teach you is those numbers are so special. How do you remember them? Sine of 30 is 1/2. Sine of 30 is 1/2. The cosine of 30 then must be the other special number, which is square root of 3 over 2. Cosine of 30 is square root of 3 over 2. Cosine of 30 is square root of 3 over 2. For the 45 degree angle, you know that they have to be the same, and that same special number is square root of 2 over 2. All right, so now we have projected for the 30 degree position and for the 45 degree position. Let's go to the 60 degree position. The sine will be the projection over here, like this. And the cosine will be the projection down here. Now look at, interesting thing, the cosine here of this, it comes right in the middle right here. Doesn't that look like about a half? Remember, for the sine, it was the sine of 30 that was 1/2. But here, the cosine of 60 is actually 1/2, right? The cosine of 60 is actually 1/2. So the cosine of 60 is 1/2. And if the cosine of 60 is 1/2, what do you think the sine of 60 will be? It's going to be the other special number, square root of 3 over 2. That is critically important. You see what's happening? For the 30 degree position, the sine and cosine is completely flipped from the 60 degree position. Same numbers flipped around. Why is it like that? It's because there's symmetry with the 30 degree position and the 60 degree position. The projection down here is about this long for the cosine of 30. But the projection over here is the exact same distance as the projection down here, but it is the sine of 60 being that same projection. That is why sine and cosine of 30 and 60 have the same numbers, but just flipped around in their positions, because the projection along the different axes, they're the same numbers, but they're just projected along different axes. But for the middle, the 45 degree positions, the projection is actually exactly the same, and that is why cosine and sine of 45 degrees are the exact same number, square root of 2 over 2. All right? Next, let's move along and look at the 90 degree position. The 90 degree position, what would be the sine of 90 degrees? Well, if the hypotenuse is here, the projection on the y-axis for sine is fully 1. So the sine of 90 degrees should be exactly equal to 1. And what would be the projection of this degree position on the x-axis? If you shine a light down, there's no projection at all on the x-axis. So the cosine of 90 degrees is 0. So as you walk around mentally the unit circle, if I ask you, what is the sine of 90 degrees? You should say, oh, it's 1. Because it has to be 1, because the sine is the projection on the y-axis, and the entire triangle lies on the y-axis, so the projection has to be 1. What is the cosine of 90 degrees? Oh, the cosine has to be 0, because in this position, there is no projection on the x-axis at all. So you see how you don't have to memorize things, you think about them. You look at where you are in the unit circle and you think about them, and don't try to memorize tables. Well, I mean, you have to do a little memorizing, but you don't have to memorize all of it. What about the sine of 0 degrees? Sine of 0 degrees, oh, that has to be 0. Why? Because the triangle, if it's at 0 degrees, the sine is the projection on y, but there is no y component, so it's 0. What about the cosine of 0 degrees? Oh, the cosine must be equal to 1. Why? Because if it's 0 degrees down here, the cosine is the projection on the x-axis, and the whole thing is on the x-axis. So really, the 90 degree and the 0 degree position, you can just get them by thinking about the unit circle. These lines of the table are really just, they come to you by thinking about where you are in the unit circle. The other positions, you do have to do a little bit of memorizing. This is how you do it. When you're at a 45 degree position, the sine and the cosines have to be the same, because the projections in the x and the y axis are exactly the same number, right? What is that special number? Square root of 2 over 2. So then we know that the sine of 45 is square root of 2 over 2. The cosine of 45 is square root of 2 over 2. Okay, we've got that. Now, what happens if we take the sine of, let's look at the 30-degree angle. What is sine of 30? Say it 25,000 times until you remember the sine of 30 is 1/2. 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 Then you think, well, what's the cosine of, the sine of 60? The sine of the other angle, not the 30-degree angle, that's 1/2. What's the sine of the 60-degree angle? That has to be the other number, square root of 3 over 2. Square root of 3 over 2. And then when you think about the other positions, you have to flip them around. Sine of 30 is 1/2, so cosine of 30 must be the other number, square root of 3 over 2. So cosine of 60 must be the other number, 1/2. And I can't really help you memorize it other than that. You need to think sine of 30 is 1/2. Cosine of 30 must be the other number, square root of 3 over 2. And then cosine of 60 is square root of 3 over 2. And cosine of 60 is 1/2. Sorry about that. And sine of 60 is square root of 3 over 2. So sine of 30 is 1/2. Cosine of 60 is 1/2. And then the other numbers pop into the chart like that. We're going to do enough problems where you're just going to memorize it, but that's essentially what you have to do. Now, notice that this, as we walk around the unit circle, the projections down here, from here to here, this is called the cosine. The projection from here to here, this is called the sine. So in many books, what you'll actually see is you will see some kind of coordinates written outside the unit circle, right? So look at the easiest one. The 45-degree position is square root of 2 over 2, square root of 2 over 2. That means the projection here is the square root of 2 over 2, and the projection here is the square root of 2 over 2. That's what sine and cosine are. That means that if this were really a unit circle, this point would have a coordinate, which would be square root of 2 over 2, comma, square root of 2 over 2. Because the x position of this point would be square root of 2 over 2, and the y position would also be square root of 2 over 2. So the sine and the cosines are also the coordinates of the points around the edge of the unit circle. So what would the point be right here? Well, the cosine of 30 is square root of 3 over 2, but the sine is 1/2. So what you would have over here is square root 3 over 2, comma, 1/2, like this. Because the cosine, which is the x value, is square root of 3 over 2, about 0.866, and the sine would be 1/2, which is this projection right over here. What do you think this point would be along the edge of the unit circle? It would be these numbers completely flipped around. 1/2, comma, square root 3 over 2. Because the projection in the x-axis is 1/2, and the projection on the y-axis, which we call the sine, is called the square root of 3 over 2. Remember, square root of 3 over 2 is about 0.866, and 1/2 is what it is, 1/2, 0.5. Now, a couple of things I'll write down here is, what would the coordinates of this point be over here? I mean, this is a unit circle. This is the distance of 1, so the x-coordinate of this point right here, the x-coordinate is 1, and the y-coordinate is 0. That's what this point is right here. So this is 1, 0. What would this point up here be? This point would be 0, 1. X, y, 0, 1. X, y, 1, 0. These other points on the unit circle are just the sines and cosines of these numbers here. The cosine is the x value, and the sine is the y value. So here's what the unit circle is that you'll see in most textbooks. You'll see the angles marked around like this, and then you'll have, in parentheses, all these things. The first number is the cosine, which is the x coordinate, or the x projection of all of these hypotenuses. And the next door neighbor component is the y projection, or the y component, or the y projection of each of these little hypotenuses there. Personally, I don't use a unit circle very much at all, because I want you to remember sine of 30 is 1/2. Really, I don't want you to memorize unit circles. Unit circles are great to have as a reference, but they're cumbersome to use. It's better to just remember the core fundamental angles and their sines and cosines. You know that sine 30 is 1/2. Sine 30 is 1/2. So then the cosine of 30 must be the other number, square root of 3 over 2. Cosine of 30, square root of 3 over 2. Then when you move to the 60-degree position, the sine of this must be the other special number, square root of 3 over 2. The cosine of that number is 1/2. So the 30 and the 60 position are just flipped around. The 45 is square root of 2 over 2 for the sine, square root of 2 over 2 for the sine. These numbers just come from thinking about where you are on the unit circle. All right, So we have filled out the entire table for the first two columns. Now I want to spend the rest of the lesson filling out the rest of the table. Do I want you to memorize the rest of the table? No. Have I ever used a table of values like this in trigonometry or calculus or pre-calculus? No. Personally, I never have. Ever. And I do mean that honestly. I have never said, hey, what's the cotangent of 45 and looked in a table? Never. Never, ever, ever. What I've done, though, is I know what these basic angles are. And I know that all of these other things are calculated from the basic angle. So that's all you have to do. You go calculate whatever you need in the rest of the table from these basic values right here. So the rest of this lesson, I want to spend filling out the rest of this table. It's going to be a little painful just because it's so long, but it gives us also a lot of practice with solving problems. All right, so the first thing I want to do is let's go to the, let's just go line by line. Let's go down and let's just fill out the rest of this table right here. So what am I going to have at the 0 degree position, right? At the 0 degree position, that's what I'm working on next. So what I need is I need to know what is the cotangent, what is the tangent of 0 degrees? Because that's the next thing in here, right? I want to calculate. But remember I told you the tangent can be written as sine over cosine. So it's going to be the sine of 0 degrees over cosine of 0 degrees. So because it's sine over cosine, sine is 0 and cosine is 1. So what you're going to get is 0 over 1. Sine of 0 is 0. Cosine of 0 is 1. What do you get? 0. So the tangent of 0 is 0. So then I will go over here and say tangent of 0 degrees is 0. That's how you use this thing. You don't memorize the tangent is 0 is 0. You calculate the sine and the cosine, and then you figure out what the tangent is. Now for the rest of this entire table, remember we know that we redo it as sine, cosine, tangent, cotangent, secant, cosecant. These go together, and then these also go together. So we're going to crank through pretty fast because I don't want to spend the rest of the universe time here doing this, but it's important for us to go through it. What would be the cotangent of 0 degrees? Well, what would that be? 1 over the tangent. 1 over the tangent of 0 degrees. Okay, so what was the tangent? We said it was 0. What's 1 over 0? In some books you'll see it as undefined. In some books you'll see it as infinity. I'm going to put it down as infinity, but just keep in mind that some books are not going to put infinity down. They'll just put undefined. So the cotangent of 0 degrees is really infinite. If you put it into a computer, it'll either tell you infinity or it'll tell you undefined. All right. Next on the list is, what is the secant of 0 degrees? The secant is 1 over the cosine, right? What was the cosine of 0? We look at the cosine of 0, it's along the x-axis there, so the projection was 1, so it was 1 over 1, which is 1. So the secant of 0 degrees is then 1. Secant of 0 degrees is 1. What's then the cosecant? The cosecant of 0 degrees is 1 over the sine of 0 degrees because of our inverse relationship. What is the sine of 0? The sine of 0 is 0. We have it right here. So then you have 1 over 0. What do you get for this? Again, infinity. Some books might say undefined. So we have infinity. So here we filled out the first row of the table. I'm going to spend the rest of the lesson filling out the rest of the table. I could just tell you what's in the table, but then you wouldn't know where anything comes from. You would think, oh, he's just a magician. He just gives me things and I'm just supposed to memorize them. No, I don't want you to remember any of this part of the table. I mean it. I just want you to know where it comes from. All right, so then let's continue. Let's crank through the rest of this guy. We've done the 0 degree position. Now let's move to the 30 degree position. We need to calculate the tangent of 30 degrees. How do you do that? Well, we know that tangent is defined as now sine over cosine. Sine of 30 degrees, cosine 30 degrees. All right, what was sine of 30? You should remember this, 1/2. Okay, what is cosine of 30? It's the other special number, remember? It's square root of 3 over 2. So you have square root of 3 over 2. Now when you invert and multiply, you're going to have, flip this guy over, 2 over square root of 3. The 2's are going to cancel, and you're going to have 1 over square root of 3. But a radical in the denominator is a big no-no. You never want it. So you write multiply by square root of 3 over square root of 3. And then what do you get in the end? You're going to get a square root of 3 on the top. you'll get a square root of 9 on the bottom, but when you take the square root, it'll just become a 3. So what you get is the square root of 3 over 3. So the tangent of 30 degrees is the square root of 3 over 3. Again, I don't want you to remember that the tangent of 30 degrees is square root of 3 over 3. Some people remember that, but I think it's a waste of time to remember that because we have better things to do in life than to memorize things. All right, what's the next thing we have to do? We're going a little fast because I want you to kind of get good at it with me. What is the cotangent of 30 degrees? The cotangent is defined as 1 over the tangent. So it's 1 over the tangent, but I just calculated the tangent, which was square root of 3 over 3. So when I invert this, it's going to be 3 over the square root of 3. Now again, I have this ugly radical in the bottom, so I'm going to multiply by square root of 3 over 3. So what am I going to get? 3 times the square root of 3. This will be square root, I'm sorry, I made one little mistake. I'm multiplying by square root of 3 over square root of 3. On the bottom, I'll have square root of 9, which reduces to 3. The 3's will then cancel, and I will have square root of 3. So let me check myself. The cotangent of 30 degrees is the square root of 3. So what do I have? Square root of 3. Cotangent of 30 degrees, square root of 3. Do I want you to memorize that? No way. I think it's a huge waste of time to do that. What is the secant of 30 degrees? The secant is 1 over the cosine. 1 over the cosine of 30 degrees. Think about it. What is the cosine of 30 degrees? The cosine of 30 degrees, the sine of 30 is 1/2. The cosine of 30 is the other number, square root of 3 over 2. So it's 1 over square root of 3 over 2. When you invert it, you're going to get 2 over the square root of 3. Exact same problem. We don't want radicals in the bottom, so we multiply by square root of 3 over square root of 3. And so then what we get is 2 times the square root of 3 over square root of 9, which reduces to 3. So you get 2 times the square root of 3 over 3. Let me just double check. 2 square root of 3 over 3. 2 multiplied by the square root of 3 over 3. The secant of 30 degrees is equal to that. All right, next up we have cosecant 30 degrees. Cosecant of 30 degrees. What do we get? Cosecant is 1 over the sine. So it's 1 over the sine of 30 degrees. What is sine of 30? You should memorize it by now. We're not even going to look at the table. It's 1/2. So 1 over 1/2. When you invert and multiply, you just get a 2. So cosecant of 30 degrees is equal to 2. All right. So we're getting close. And I'll take a little bit of a break from the monotony of doing what we've done to kind of skip down the table. We're going to fill it all out, but let's skip down to the easy lines at the bottom here. Remember, to calculate the tangent of anything, it can be written as the sine divided by the cosine. The sine down here is a 1 and the cosine is 0. So the tangent of 90 degrees is sine divided by cosine, which is 1 divided by 0, which is infinity. Right? So the tangent actually works out to be infinity for 90 degrees. All right? The cotangent, remember, the cotangent is 1 over the tangent. So it's 1 over this. What is 1 over infinity? 1 over infinity is like 1 over an enormous number. So 1 over infinity is going to basically be equal to 0. So the cotangent of 90 degrees is equal to 0. What is the secant? The secant is 1 over the cosine. 1 over the cosine. The secant is 1 over the cosine, but the cosine was 0. So 1 over 0, again, goes back to being infinity. And what is the cosecant? The cosecant is 1 over the sine, but the sine was 1. So 1 over the sine is 1 over 1, which is 1. So you see, now this table is almost completely filled out. We do have more work to do, but we're going to crank through it. Okay? Let's go do the last part. Let's tackle the 45-degree area right here. We're going to look at 45 degrees. Right? We need to first calculate the tangent of 45 degrees, but we now know that tangent is sine of 45 over cosine 45. I want you to know by now that the sine of 45 degrees is square root of 2 over 2, and the cosine is also square root of 2 over 2, but if you forget, just go down here to 45 degrees, the sine and the cosine are both square root of 2 over 2. So what do you get? Square root of 2 over 2 divided by square root of 2 over 2, and you get a big fat 1. So as ugly as this looks, the tangent of 45 degrees actually works out to just be the number 1. Okay, and I guess I can cheat a little bit and say, well, if the tangent is 1, what's the cotangent? The cotangent is just 1 over the tangent. I mean, that's from the trig, that's from the rainbow. So 1 over the tangent is just 1 over 1, which again is equal to 1. So the cotangent of 45 is also equal to 1. All right, now let's move along. What is the secant of 45 degrees? If you go back to that rainbow thing, you'll see that that's equal to 1 over the cosine of 45 degrees. All right, 1 over 45. Let me catch up to myself. 1 over 45, yeah, 1 over cosine 45 degrees, yeah. All right, so what do I have then? What is cosine of 45 degrees? Remember, cosine is square of 45 degrees is square root of 2 over 2, just like it's the sine. So 1 over square root of 2 over 2, when you flip it over, is 2 over square root of 2. We don't like the radical in the bottom, so you must multiply by square root of 2 over square root of 2. And so what you're going to then get is 2 times the square root of 2. This will be square root of 4, which comes out to 2, which means the answer is actually square root of 2. So the secant of 45 degrees, works out to be, let me just double check myself, square root of 2. Hey, I make mistakes all the time, so I just want to make sure I'm not doing a huge mistake for you guys. All right, last guy here, cosecant of 45 degrees is 1 over the sine of 45 degrees. How do I know that? Comes from that trig rainbow thing. But I know that the sine of 45 degrees from that table, again, is the square root of 2 over 2. It's exactly the same business as what's been going on. I could go through the whole thing again, but I'm going to end up with the square root of 2 again. All right, so in this guy, it's going to become square root of 2 for the final answer. All right, now let's crank through the last bit of the table. We have the 60-degree position. What is the tangent of 60 degrees? It's the sine of 60 degrees divided by the cosine of 60 degrees. Now let's try to do this without the table. The sine of 30 is 1/2. But this isn't 30, it's the other angle. So it's sine of 60, which is square root of 3 over 2. And then it's cosine of 60, and that one, when you think about the table, the cosine of 60 actually is equal to 1/2, right? Because the cosine of the sine of 60 is square root of 3 over 2, so the cosine must be 1/2. So they're opposites of each other. They have to be opposites of each other because they're the opposite operation. So what are you going to have? Square root of 3 over 2 multiplied by 2 over 1. Flip and multiply. By the way, before we go any farther, the sine of 60 degrees was square root of 3 over 2. The cosine of 60 degrees was 1/2, so it's this divided by this. So this divided by this. So what are you going to get? So what you're going to get after this cancellation of the 2's is square root of 3. So the tangent of 60 degrees is the square root of 3. Just a big fat square root of 3. All right, next what we need to do is figure out what would the cotangent of 60 degrees then be. It's going to be 1 over the tangent of 60 degrees. We just figured out what that is. It's square root of 3. Now we could leave it like that, but we never do that. So we're going to multiply by root 3 over root 3. And so what we're going to get then is the square root of 3 on the top. This will be square root of 9 on the bottom, which comes out to be a 3. So you get square root of 3 over 3. Square root 3 over 3 for the cotangent of 60 degrees. All right, cruising along, almost done. Hang out with me. We have the secant of 60 degrees. If you go back to that rainbow, the secant comes out to be the 1 over the cosine of 60 degrees. What is the cosine of 60 degrees? It's 1/2. 1 over 1/2. How do I know that? It's because I know that sine of 30 is 1/2. So cosine of the other angle must be 1/2. Cosine of 60 degrees is 1/2, just like the sine of 30 is 1/2. You just have to mull these in your mind enough to realize that sine of 30 is 1/2. So cosine of 60 is going to be 1/2 because the cosine the sine of 60 has to be square root of 3 over 2 to be opposite of this one, so this one has to be opposite of that. Anyway, everybody has their own ways of remembering these things. I remember sine of 30 is 1/2, sine of 60 is square root of 3 over 2, so then the cosine of 30 must be square root of 3 over 2, and the cosine of 60 must then be 1/2. So the cosine of 60 is 1/2 right here, and when you flip that over and multiply, you just get the number 2. So what is the secant of 60 degrees? It's just going to be the number 2. All right, finally, one more item here. We have the cosecant of 60 degrees. We have the cosecant of 60 degrees, which using our little trig rainbow is the sine of 60, 1 over the sine of 60 degrees. We know that sine of 30 is 1/2, so the sine of 60 has to be the other number, which is square root of 3 over 2. And you can look at the table and verify that. When you flip it over, you'll get 2 over square root of 3. But we want to get rid of the radical by multiplying by root 3 over root 3. So you get 2 root 3 over, this is the square root of 9, which comes out to 3. 2 square root of 3 over 3. Let me write that down. 2 times the square root of 3 over 3. All right, now let me take a second just to check myself because I make mistakes too. So we have sine, cosine, tangent, cotangent, secant, cosecant. We have 0, 1, 0, infinity, 1, infinity. 1/2 square root of 3 over 2, square root of 3 over 3, square root of 3, 2 square root of 3 over 3, and 2. Then we have square root of 2 over 2, square root of 2 over 2, 1, 1, square root of 2, square root of 2. Then we have square root of 3 over 2, 1/2, square root of 3, square root of 3 over 3, 2, 2 times the square root of 3 over 3. Then we have 1, 0, infinity, 0, infinity, 1. Now look at this table and tell me it doesn't look crazy. It looks crazy to me. I understand everything in this table, but it still looks crazy to me because there's radicals everywhere. Sometimes they're, sometimes a 3 is on the bottom and sometimes there's nothing on the bottom, and it's just crazy looking. So stop looking at the entire table and trying to memorize it. It's a waste of time. I did all of these mostly so that you could get practice with it, so that you know where the table comes in play, but really the only things you need to remember is this stuff. This stuff's what you need to remember, and really this line and this line are easy because we know when we walk around the unit circle, the projection in x, the cosine of 0 must be 1, but the sine of 0 must be 0 because the projections work out that way. For this at 90 degrees, we know the cosine of this 90 degrees must be 0, and the sine of 90 degrees must be 1. So we already know these lines of the table, so really it's just these 6 values you need to know. The 45-degree values are the exact same number because the projection is exactly the same in both cases for sine and cosine, and that special number is square root of 2 over 2. So the only things you have to really remember too hard is how to handle sine of 30 and cosine of 30, and sine of 60 and cosine of 60. Remember, sine of 30 is 1/2. Cosine of 30 must then be the opposite one, square root of 3 over 2. Then sine of that opposite angle must be square root of 3 over 2, and the cosine of that one must be the other number, which is 1/2. And we've talked about how that all works out. We also talked about how the sine and the cosine are basically the projection, so they're the coordinates of the points on the unit circle. If I drew a unit circle and looked at the xy value here, it would be this, comma this. If I looked at the value of this point right here, it would be this, comma this in decimal form. If I looked at the coordinate here, it would be this, comma this, just like this is 0, 1, and this is 1, 0. Now in future lessons, we're going to go all the way around the unit circle and fill it out all the way around, but let me give you a secret preview. It's not going to be hard because it'll be the same numbers. Look at the symmetry. Over here, the projections will be very, very much the same as they are in quadrant 1. It's just that sometimes we'll have negative signs because of how it's being projected around, but the actual numbers, the square root of 3 over 2 and all that will be the same all the way around the unit circle. One last thing I want to talk about. I told you I would do it, and so I don't want to lie to you. I told you to believe me that this point here, that the sine and the cosine was equal to this, comma this. If this really is a unit circle, then the x value forms a triangle and the y value, the x and the y value form the legs of the triangle, and this is the hypotenuse. So that means that if I take the square root of 2 over 2 and I square it, and I add it to the square root of 2 over 2, and I square it. These are the sides of the triangle. These are the values I'm telling you there are. What do you think they're going to add up to? By Pythagorean theorem means x squared plus y squared must be the radius or the hypotenuse squared. But the hypotenuse is 1 for a unit circle. So it should be equal to question mark 1. Is it? Let's check it out. Square the numerator, get rid of the radical. It'll be a 2 over a 4. This will get rid of the radical, 2 over 4. And this is going to be, of course, 4 over 4. Which is equal to 1. Exact check mark. All right, let's take a look at another one. I told you, hey, trust me, the cosine was square root of 3 over 2 and the sine was 1/2. Let's check this one. If it really does form the legs of a triangle, then this leg of the triangle is square root of 3 over 2. And this leg of the triangle is 1/2. And the hypotenuse is 1. So what we should have then is the square root of 3 over 2 squared plus 1/2 squared equals question mark. It should be equal to 1. So if we get rid of the radical here, it'll be 3/4, getting rid of the radical and then squaring the bottom, plus square this, you'll get 1/4. What do you get? 4 over 4, which is equal to 1. Check. So these numbers, which seem like they come out of nowhere, square root of 2 over 2, and square root of 3 over 2 and 1/2, it seems like they come out of nowhere. But here's the secret sauce. Those numbers are the special numbers that work out with Pythagorean theorem so that at a 30-degree angle, the legs of this triangle have to be 1/2 in this direction, and it has to be square root of 3 over 2 in this direction in order to give you a hypotenuse of 1, right? For this triangle, in order to have a hypotenuse of 1 at this angle, this leg must be square root of 2 over 2, and this one square root of 2 over 2. The Pythagorean theorem dictates these numbers is what I'm trying to tell you. They have to go in and work, so these special numbers that seem like they come out of nowhere, they don't come out of nowhere, they come from the Pythagorean theorem because the hypotenuse of all of these triangles is 1. Same thing up here. You have this guy is a 1/2, and this guy is a square root of 3 over 2. Same number, so Pythagorean theorem is just addition, so it doesn't matter the order, and so that's why the numbers up here are just reversed of the ones down there for the similar reason. Last thing I'll say is I kept telling you the cosine is the chopping in the x direction, and the sine is the chopping of the hypotenuse in the y direction. I kept telling you that a lot, but I made a very special point to tell you that it was the chopping in the x direction, assuming the length of the hypotenuse was 1. The sine was the chopping in the y direction, assuming the length of the hypotenuse was 1. The reason I said that is because here the hypotenuse really is 1. So you can see that the chopping factors are all listed on the edge of the circle because if the hypotenuse is 1, those are the projections if the hypotenuse was 1. And so we use those factors, chopping factors, whatever you want to call it, when we have larger triangles with hypotenuses larger than 1. That's why we can multiply them times the larger triangles to chop them in the x and the y direction, because this is kind of like the baseline. When the hypotenuse is 1, these are the kind of the chopping factors or the projection factors, the base factors. And if we have triangles larger than that, like we were doing earlier, we just multiply by the hypotenuse and it chops it down in the x and the y direction. All right, I feel like I've done enough talking. I know this has been a really long lesson, but it really is one of the most important lessons in all of trig and pre-cal, because the fundamentals of this feed into everything else. The rest of this unit circle comes from this, and all the topics beyond come from this. I really do recommend that you watch it twice. I've talked until I'm a little bit hoarse. I've said a lot. Please go back and listen to it and try to internalize. If I misspoke every now and then on sine and cosine of 30 and 60, I apologize. I tried to do my best, but I'm a human also. So if you see something in the table and I said something a little different, just keep in mind the table is correct. I want you to watch this a few times. Follow me on to the next lesson. We're going to continue conquering the topic of algebra and trig and pre-calculus and the topic of angles and trigonometry.